Started. We'll go from current slide. And, all right, before we get started on that, I had a few issues here. First, everybody done the student course evaluation yet? Please remember to do it. Okay, you do have until August the 8th. But guess what? On August 8th, I will not be here to remind you to do your student course evaluation. So please get those done sooner rather than later. If you want to wait to see what the score is, you can do that, but then shortly thereafter, do the student course evaluation, please. Okay, we value those. All right, so that's done. Now, the rest of the announcements are basically summed up with how we're going to finish the term. Okay, and here's my best approximation of how it's going to go. Okay, today we have class. I have office hours today from about 5:30 till 6. Okay, now let's talk about tomorrow then. Tomorrow, and some of you, this is important because tomorrow's class is Nolan's in that class and so is Carlton. I have office hours from 8 to 8:30. And then I'm in class from 8:30 till 10:45, and then I have office hours. Now here's why this is new, not new, but different. For much of this month, anyway, my Tuesdays and Thursdays have been eaten up by having to go to the Birmingham campus for one reason or another. That, I hope, knock on wood, is all over with, mostly over with, anyway. So, tomorrow, after my 10:45, that class is over at 10:45, I should be in my office from 10:45 or shortly thereafter until around 4:15. Now, earlier in the term I said 4:30, but I found that if I left here at 4:30, I barely make it to Birmingham in time. We always got started late. Not that it seems to matter much because I got started late today too, but I try to be there a little earlier. So I'll be leaving by 4:15 or try to leave by 4:15. So I have a whole big chunk of office hours tomorrow, and that same thing on Tuesday too, 8 to 8:30, 10:45 to, now on Tuesday, 10:45 till about 4:15. Okay, so those are going to be my biggest chunks of office hours left. All right. Monday, when this class meets again, there are several things that need to happen. Number one, I hope to have all of your papers in by then. That includes your research paper and all your tests. Okay? Research paper, if I don't have it in by Monday class time, you start losing points on the research paper. Okay? Your test, that's test 1 and 2, right? That's what we've had. I don't have those in by Monday, they become zeros. Okay, so please get your first 2 tests in, because I want to turn back all of your tests. I can't return your research papers because periodically they ask for samples of student writing, so I have to hang on to those. But your first and second test I want to give back to you on Monday. Okay. Same thing on Tuesday. Research papers are due on Tuesday, and all your tests up to that point will be on Tuesday. Now, that's for those folks. So let's talk about when you can do that. I'm sorry. Yeah, that's Monday. Okay. Now, Tuesday, again, I already said what my office hours are. Let's move on to Wednesday. Monday and Tuesday are the last 2 days of class. Monday, Wednesday classes on Monday, Tuesday, Thursday classes on Tuesday. Okay? Now, Wednesday is the finals day, technically, for this class. Okay, now here's the bad news, folks. I did not get your test run off or made up for this last section. I wanted to get it done, but I was eaten up all day yesterday afternoon on the Birmingham West campus. I mean, one thing after another just kept interfering. I could not get it done. So that means Monday I'll be giving you your final exam, the last chapter test, chapter 14 test. Sorry you only have a few days to work on it, but try to get everything else done so you can free up time to get that done. Okay? So, the last class, Ricky was in that, and I was able to get that one run off, but not this one. Okay. I think I'll have yours done tomorrow morning. Hope so, anyway. All right. So, Wednesday, I will be on this campus from 8 in the morning, and I wish I could say until 6 in the evening. But guess what? They've called a meeting for Wednesday afternoon during final exams, so I've got to be on the Birmingham West campus at 1 o'clock. So I'll be leaving here on Wednesday by 12:30. Okay? So if you don't get me your test by 12:30, slide it under my door. Unless it's more convenient for you to go to the Birmingham West campus. If it is, I'll be over there for the rest of the day. Now, when I'm in the meeting, you can return it to Ms. Rose Saxton, who is my boss's secretary in room B122. That's the academic building, room 122. After 3 or so, I should be in that office, and so you can turn it into me. But if that's not convenient for you and you want to turn it in here, slide it under my door. Does everyone know where my office is? I'm going to remind you of where my office is. You go out the door here, hang a left, go down that little half flight of stairs there, go almost to the end of the wall, end of the hall there, and it's the last office on the left, 265. Okay? So if you can't find me in the classroom here, which I probably won't be in the classroom much on Wednesday, try my office. So try my office first, in the classroom, in case I'm up here. Okay, so that's Wednesday. Now, if you don't catch me in person, fly down on my door, and I'll get them graded, knock on wood, Thursday morning. All right, now let's do Thursday. Thursday, no classes again. However, I'll be in the office from 8 o'clock in the morning until around 4 o'clock in the afternoon. See, I've got to go to the Birmingham East campus to pick up the finals from that class. Okay? So, if you don't get me everything you've got to do by 4 o'clock on Thursday, you've either got to take it to the Birmingham East campus now, not the West campus, East campus, and give it to me in person there. And I'll be in the nursing building, which is on the East campus, that's across the Wilson Road from the West campus. It's the Ethel Hall building, the nursing building, and in room 214, second floor, room 214. If you don't get it to me there, I'm not coming back here to the Bessemer campus until fall term begins. So you will not get a grade, you'll get it incomplete, and I won't be able to grade your stuff until afterwards. So I've got to have it. If you're going to be waiting until Thursday to turn it in, you've got to have it before 4 o'clock here on this campus or before 6:30 on the Birmingham East campus. Is that clear? Okay. I haven't gotten approval to take off Monday, but I want to request Monday off so I can have a full weekend. We've got a lot of things to do on the term break. Okay? Any questions on that? Okay. Research papers and all your other tests are due by Monday, Tuesday for those folks, and your final exam is due technically by Wednesday, but definitely by Thursday. If you're going to return it to this campus, be sure you have it done here to me before 4 o'clock on Thursday, because I've got to go to the other campus. If you want to catch me over there, catch me before 6:30 on the other campus. In Birmingham East campus, Ethel Hall building, room 214. All right. Any questions on any of that? All right. Now, any questions on calculus? Okay. I need some white space to work. We're on okay. In chapter 14, multiple integration, 14.5 is surface area. This is 14.6, but there aren't any more slides in 14.5, so I came to this one. Let's see if I can find, that's probably going to have the most white space. So let me go back and do here. I'm going to do, we're on page 1008, multiple integration surface area. And this is example 3, bottom half of page 1008. All right. And this, yuck. Okay. For some reason, my computer keeps blinking off. That stays on, but my computer's blinking off the monitor. Okay. Now, don't sweat this one too much because I doubt if you're going to have this, but it is a way that you can do some of these problems a little easier. Find the surface area of the paraboloid. Here's your paraboloid. Let me get my pen set up. Okay. Y is equal to, no, I'm sorry, Z is equal to 1 plus x squared plus y squared. Okay, that's a paraboloid, okay, that lies above the unit circle shown on the figure in the text, which if you don't have the text, here's kind of what it looks like. Okay, now, I don't do three-dimensional drawings well, very poorly in fact. X, Y, Z. Okay, let's do a unit here, a unit there, a unit back there, and a unit over here. Okay, and this will be approximately what that unit circle looks like. Not a very good circle. Okay, now I didn't leave enough room in Z. Sorry about that. Z starts at 1 here, and it goes up like this, and like this, and like that, and like that. So here's your paraboloid up here. Okay? Kind of. Okay. It says find the surface area of that paraboloid that lies above the unit circle shown here. So there is 1, 0, 1, 0. 1, 0, 0, 0, negative 1, 0, and negative 1, 0, 0. Okay. And this is at 0, 0, 1. Okay, that point right up there. Okay. Now, find the surface area of that paraboloid. Now, now I wish I had left the state in 14.5, even though there wasn't the slide on it, but let me give it to you now. Here's the definition of surface area. I'm going to name it capital S. And that's going to be the double angle over some region R. Here is our region R, the unit circle down there, times your ds, which is the incremental parts of your surface area. And that is the same as the double integral over R, same R, of the square root of 1 plus f sub x, they write out of xy, squared plus f sub y squared of xy. They just call it dA, which basically is going to be your dx, dy, and it doesn't really matter the order. Okay, so there is your definition of what surface area is. And if you recall, it looks fairly similar to what your arc length was in 2 dimensions. Your arc length was the square root of 1 plus f prime squared.
Isn't arc length in this 1 plus the derivative of x?
Yeah, f of x squared. Yeah. Square root of x. Yeah. So this is very similar, only we got partial derivatives here. So obviously one thing you've got to do, and by the way, this is also called the f. You could call it z. It doesn't matter what you call it. Just don't call it suit. No, never mind. What is, let's call it z. Let me go back and change this to z's here. That will make more sense. Okay. All right. Z sub x and z sub y squared. Okay. So let's first do, what is your z sub x? Here. Second? 2x. Okay. What's your z sub y? 2y. Perfect. Okay. So when you do this in the integral, so far I'll leave it just r for now, and that would be the square root of 1 plus 4x squared plus 4y squared dy. I'm sorry, dA. Okay. There we go. All right. Now, not the best way to work this problem, because if you were doing this, you have to have your dx, dy, then you have to go from one side of the circle to the other side, back and forth, and you have square roots and all sorts of weird things there. The better way to do this is to do it in terms of polar coordinates. Now, what are some, in your polar coordinates, what are they? Polar coordinates? R, theta, and z. So the z is going to be the same, no sweat there. So let's write this form here. Z is equal to, okay, well, I can't find my, there we go. Sorry. How is r related to x and y? You remember?
X squared plus y squared.
R squared, you got it. X squared plus y squared equal r squared. Okay, I already got my equal r squared, so I don't need it again. Which makes for a very interesting situation here. Z is equal to 1 plus r squared, right? And then when you do the integral down here, this is equal to the square root of 1 plus 4 r squared, right? Where the r went to, I don't know, okay? Now, what is your dA in polar coordinates? R dr d theta, exactly, okay? So basically what we've got is the double integral over this region R, okay? Now, let's talk about that region R. This is the unit circle here. That's your region R. How would you define that in polar coordinates? Okay? Let's write down what we know. This is the square root of 1 plus 4r squared. And you said r dr d theta. Now, I just did it the way you said it. If we were doing the yeah, the limits.
It would be from 1 to 0 for the r, and then for the d theta, we go from 0 to pi.
Okay, exactly. So, I think it's probably all right to do them that way. So you said 0 to 2 pi on your theta, and your r is going from, where did you say?
1 to 0.
More like 0 to 1, isn't it?
Or, yeah.
Yeah, lower to higher. Okay. Now, how about doing the integration? Do you see anything that's going to be helpful there?
U substitution.
Okay, and what would you substitute?
U equals 1 plus r squared.
No, 1 plus 4r squared, right? Yeah. But good idea, okay, 4r squared. Then what's the next step?
Take the derivative.
du is equal to 8r dr. Okay. Well, we have an rdr but not an 8rdr, so let's divide both sides by 8, and that will give you your du over 8 is equal to rdr, which is what we want. Okay. So let's do our limits again. 0 to 2 pi on your theta. And now we have what would be your integrand now?
It would be u to the 1/2.
Okay, u to the 1/2.
Oh wait, we put in front of that interval.
Put a 1/8 in front.
Yeah.
Perfect.
And then we put du.
Second,
du.
du d theta. Okay. Now, what have I left off?
R.
What r?
Because
You went from r's to u's. We want the limits, but not in terms of r, in terms of u. So let's go to our definition here. When r is equal to 0, this is what this stands for. R equals 0, what's your u? 1. When r is equal to 1, what's your u? 5. Okay. Now we have it, which is a big boo hiss, I think, but we've still got it. Okay? Now, what's the 1/8? 0 to 2 pi is still good. Okay, and what is your antiderivative of u to the 1/2?
it is 2/3.
2/3 u to the 3/2. Okay, and then that would be, oh, left off my limits again. Okay, and this is going from 1 to 5. U's going from 1 to 5. U is, aren't you? Okay, and then your d theta here. Okay, now that's an equal sign there. It didn't show anything but 1. Okay, let's do that evaluation, which is miserable, but it's okay. That would be 1/8, the integral from 0 to 2 pi. What would you do here? Let's go on and pull out the 2/3 because we're not going to use it for anything else. So that makes it, the 2 will go in the 8 4 times. That would be 1/12 exactly. Okay, that'll be a 1/12 down here. Okay, get that out of the way. And then 5 to the 3/2 power. Okay, let's just leave it like that. 5 to the 3/2 power.
Wouldn't that be 25? 5 to the...
It'd be 125, the square root of 125. Because you raise the 5 to the 3rd power, take the square root of it. The denominator is the root.
Yeah.
The numerator is the exponent.
You get
Whatever it is, something
11.1.
that sounds very reasonable. Okay, we'll hang on to that. We'll come back to it later. Minus, that's when you substitute it. We pulled out the 2/3. When you substitute in a 1, what do you get? 1, right? Okay, and this will be then times d theta, and that'll just be some number. And if my memory's right, you said it was something. Oh, I'm looking at the wrong one. I was going to say, how can that be? I said 5 to the 3/2 power. They do 5 root 5. That's fine too. Minus 1, and then you integrate that. That's just a number. So I'm running out of room rapidly here. So let's do it what they called it. 5 root 5, that's 5 to the 2/2 power is 5, times 5 to the 1/2 power is root 5, minus 1, divided by, sorry, my screen just disappeared on me. There we go, we got it back. Minus 1 over 12. I'm sorry, this thing's going nuts today. That's the coefficient. Now all we've got left is a antiderivative of d theta. And what's that? Theta, okay? So this will be times theta evaluated from 0 to 2 pi. And of course that will be 2 pi, okay? And when you do 2 times this over 12, that would make that a 6, so I'm just going to wipe out that. And that would be, your final answer then is 5 root 5 minus 1 times pi divided by 6. That's your answer, I hope. Yeah. Pi times 5 root 5 minus 1 divided by 6. And they said that's approximately 5.33. Now let's see if that made sense. If my memory's right, you said this was 11 something, right? Okay, subtract 1 from it, you got 10.18. Divide that by 6. Well, wait, let's do it this way. Pi is just a little bit more than 3. So this is going to be multiplied by something about a little bit less than 1/2. And 1/2 of that would be 5 point something. Yeah, that seems pretty good. 5.33. That seems like a reasonable answer. Okay? Did that make sense? All right. Not a terribly awful problem, especially if you get it into polar coordinates. And it worked out so nicely because this is related to r. This, of course, is related to r. You know, it worked out really nicely. All right. Now, all right, to clear this sink. Okay. Let's now do example 4. Find the surface area S of the portion of the hemisphere f of xy is equal to the square root of 25 minus x squared minus y squared. Now why is that a hemisphere? Because your coefficient here is a +1. So that's the upper half of this sphere. Radius 5. Okay? That lies above the region R bounded by the circle of, so your R is the x squared plus y squared equal to 3. It's less than or equal to 3. Okay? Now I'm going to have to draw a picture of this, but let me just write it down. So you've got x squared plus y squared is less than or equal to 9. Okay? Now, let me approximately give you, okay, this is radius 5, so we'll do 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay. Now, your hemisphere, and then let's get a few back here too. 1, 2, 3, 4, 5. A few back here. 1, 2, 3, 4, 5. Okay. So your hemisphere is going about like this. This is a pretty ugly circle. That's of radius 5. The base of it. Your hemisphere goes up to 5 here, and down to 5 here, up to 5 there, and down to 5 there, and that's your hemisphere above the top. But we're not interested in the entire hemisphere. We want the surface area bounded by the circle x squared plus y squared is less than or equal to 9, so that would be 3, 3, 3, and 3. So here's the circle that we're interested in. Okay, so that means up here, this is the portion of the hemisphere, just this part up here. They drew it pink in the book. That's the surface area we're interested in. Okay, so This is your function f of x, y. Now, of course, if you remember what the surface area is, S is equal to, what was that formula again? Double integral over, now this is your region R in here, inside 3. R of the square root of 1 plus f sub x squared plus f sub y squared dA. Okay? Now, it sure seems to me this is another one that would be far better to go to polar coordinates to do. But they don't do that yet. Okay? I don't know why. Okay? Well, I think we'll see why in just a minute. Okay? So we need to get our f sub x. So what is your f sub x of xy? Second? Negative 2x is what you said? Okay, I can't hear well. Negative 2x. Okay, you're doing f sub y now. Let's just do with f sub x. What's that?
Are we doing the square root, or are we doing that?
Yeah, we got to do the square root. We've done the chain rule part, but we haven't done the square root part. What would that be? Second? Let's rewrite this, hopefully be helpful. 25 minus x squared minus y squared to the 1/2 power. Okay, let's try it now. 1/2, so that's going to wipe out the 2 there, right? 1/2 what? That thing there, 25 minus x squared minus y squared to the negative 1/2 power. So another way of looking at this would be negative x over 25 minus x squared minus y squared, okay, to the 1/2 power, if you put it downstairs. Okay? How about f sub y? Yeah, same thing except with a y in there. Minus y over the square root. I put it as square root, you didn't have to. 25 minus x squared minus y squared. Okay. What's the next thing you're going to have to do? You found your f sub x and f sub y. You got to square them. So your surface area here will be the double integral over that region R of the square root of 1 plus, and what would this be? Oops. When you square your f sub x, what do you get?
Well, the square root of the bottom goes away, so you just get x squared.
X squared over 25 minus x squared minus y squared.
And then
plus y squared over 25 minus x squared minus y squared. All right. And then that's going to be times your dA. All right. Now, here comes a place that's a little bizarre then. Okay?
Could you write it as 1 plus
All
r
right.
squared over 25 minus r squared?
Say that one more time.
Could you rewrite it as 1 plus r squared?
Or minus r squared.
Well, the top.
Oh, up here.
Yeah.
Oh, okay, got it. Yeah, except that you got to get it under the same denominator first.
Yeah, don't they have the same denominator?
These two do, but that one doesn't. Oh, you mean just that part? You mean 1 plus?
Yeah, I'm saying.
Okay, got it.
Yeah.
Okay, so let's see if that will work. We were going to go to that, but I hadn't quite decided. So let's just do r then. And you're right, this will be the square root of, and for some reason that introduced a weird line here that just wiped out everything else. Square root of 1 plus r squared over 25 minus r squared. Is that what you were getting at? Okay, then you're going to have to change your dA to, or make your dA, what? R dr d theta. Okay. Now, that will be over this region R. Okay. Now, to get that under the same denominator, let's come on out here and continue doing that. Okay. You need a 25, or let's put the square root of 25 minus r squared plus r squared over 25 minus r squared. Do you follow that? Yeah, multiply this by 25 over 25. That gives you 25 minus r squared plus r squared, which basically, those add to 0, okay? And then what you have here is the square root of that, and this is your d, well, we're going to get it back to r d theta. Well, r d theta. Now this r is not under the square root sign, okay? All right, now, so let's see what that yields us. Double integral, and this time, drives me nuts here. Okay, we're going to get to r's and thetas in a second here. The square root of 25 is just 5, so we can pull the 5 on the outside here, and then we have r dr d theta is all that's left in the numerator, and the denominator is 25 minus r squared to the 1/2 power. Right?
So wait, you took out the numerator?
I took out the numerator, which is a 5. Okay, because you see, the square root of 25 is 5, so bring that outside, and then you have 1 over this. Right? Got it? Follow? Okay. Now, I need my limits on my r's and my thetas. What's r's going from?
0, 5.
Not this part here. 0 to 3. The big one goes 0 to 5, but you're only doing this part up here, which is 0 to 3. This right here. R squared is less than or equal to 9, which is r is less than or equal to 3. Okay, and then your theta, of course, is going from 0 to 2 pi. Okay? Now, how might you proceed with this? Hint.
Well, can you just take the interval of that and it's just going to be L1? It's not?
Wait, maybe. Okay.
I don't know about the R.
Yeah, it's going to come up being an LN. Do you know what the LN is going to be, or do you need to work it out? Don't grind the gears too much. Go on and do your R substitution, U substitution.
Yeah.
What would that be?
That would be 25 plus
Minus
R squared.
R squared. Okay, then du is equal to
Negative 2
what?
dr.
dr. Okay. Now, let's go back to this then. Your integral, 0 to 2 pi is going to be fine. This one we're going to have to change the limits, so we'll get to that. Oh, and we don't need a -2 there, so let's divide by -2. Okay, and now we get the RDR where we want it to be. This is just takes off and goes somewhere. Okay, so we're going to have a -1 over 2, -1/2. Okay, what we have now up here is a du. Yeah, and what would that be?
When u equals 0.
When r is equal to 0.
R equals 0, it equals
25.
And when r equals 3, it equals 16.
No, 25 minus 9 is 16. Okay. All right, we'll come back to that in just a second, and this will be over u to the 1/2, right? Second? We'll fix it, okay? And this will be then a d theta at the end. So how are we going to fix that? What doesn't look right about it? Yeah, you got the numbers reversed. What happens if we reverse the numbers? What does that do for us? Yes, so now that will be 1/2. So this is looking much better. The integral from 0 to 2 pi on your thetas, if I could get it to right, okay. For some reason my integral sign just disappeared, and it won't come back now. It comes back 2 or 3 times, okay. And this one will now be 16 to 25. Okay, and I do want to change that to be a u to the -1/2 du, and then do my d theta. If it'll ever write. There's, yeah! Okay. I think it's there. It keeps flicking out on me. Okay, now I need to erase some stuff somewhere, and might as well go up to the top and start erasing there, because I don't think we need that anymore, do we? So let's erase this, because I just don't have enough room to write. If I could get it to erase. Well, maybe one day it will erase, but it's sure not doing it now. And I think I'll erase my graph while I'm at it. I hope I won't regret that later. I regretted writing it to begin with, so. Okay. Why some of these are still left, I have no idea. I think that's gone. Okay. Now, let's get back to our thing here. It's a 1/2. Outer integral is 0 to 2 pi. Let's do this one. What's the antiderivative of u to the -1/2?
Would it be 2u?
Second? 2u to the 1/2. Okay? And that's your du. Wait, we don't need that. We just did the antiderivative. Okay? We'll evaluate this from 16 to 25. And then we'll do our d theta. If it ever shows up, which it isn't showing up. It shows up several screens later. Okay. All right.
Could we take that 1/2 and that 2u?
Yep. Sounds like a good idea. Yep. So this will now be the integral from 0 to 2 pi. And when you do the square root of 25, what do you get? 5 minus 4. Good deal. D theta. So this will be the integral. Oh, we don't need to do that anyway. I will do it. 0 to 2 pi of d theta. And what would that be? Second? 2 theta. I mean, no, you're right. Theta evaluated from 0 to 2 pi. I was going on and doing the evaluation. This will be what? 2 pi. I think. I hope. Let's see. Oh, wait a minute. Somewhere along the way here, I forgot about my 5. Remember the 5 that was there? So this would be a 5 halves here, and a 5 halves here, and a 5 halves there, and this would then be a 5 because the 2's went away, and this would be a 5, and this would be a 5, so this would be 10 pi. Sorry. I put in the 5 there, we talked about it, and then I completely forgot about it. So 10 pi is your answer. Okay? All right, they do a little blurb at the bottom that I really don't see why, but it's fine. And you're doing a portion of the sphere, so they did it that way. That was example 4. Let's now finally move to example 5. Boy, these are taking longer than I wanted them to. Sorry, I should have asked if there were questions before I erased it, but I erased it. Example 5. Approximating the surface area by Simpson's rule. Okay? Boy, we thought we were through with this, didn't we? Says find the area of the surface of the paraboloid f of xy is equal to 2 minus x squared minus y squared that lies above the square region bounded by -1 is less than or equal to x is less than or equal to 1, and -1 is less than or equal to y is less than or equal to 1. Okay? Now they show the figure in the text, and it looks like a tent that you would take to a baseball game or something like that, kinda, a little bit, sort of. Okay? So I'm going to try to draw this, though it's going to come out really poorly, I'm sure. Okay? This is your x, this is your y, and this is your z. Okay? Now, I haven't, there's at least one thing I see right now, it's not good, but we'll deal with it. We'll do 1 here, -1 here, here, and a -1 here. Okay? And we want to do 1, 2 here. So we're going up to this place here, and this is going to come down to that, down to that, down to this one over here, and down to this one in front, and this is going to be your paraboloid. Okay. With a problem here is that the y's are going from, I didn't quite draw those right. Let me go back and change that. Yuck. Okay. Let me try to get that one more time here. Yuck. Miserable. Okay. I tell you, I hate drawing these things. Okay. Now, what we really need to do is do your square here. That looks more like a rectangle, but let's just pretend it's a square. Okay, and this is going up to 2 here. These are going out to 1. So here is where your paraboloid goes. From here to here, up to there, and down to here. Okay? Those are in place. Now what happens is you cut off this part of the paraboloid, that part of the paraboloid, that part of the paraboloid, and this part of the paraboloid. So you have, this is your tent part here that goes down to there. That's an ugly, ugly, ugly drawing. But just imagine you can figure out what it's doing there. Okay? Now, remind ourselves, what's the surface area?
1 equals...
This is your R down here.
1 plus f sub x squared plus f sub y.
So what's one thing you got to do? Take a partial with respect to x, and that's going to be negative 2x, and you're also going to need the partial with respect to y, which is negative 2y. Perfect. Okay, so let's rewrite our integral. Goodness gracious, I can't write. Equal to the double integral over the region R. I write something in and it disappears. I don't know what's going on here. And this will be the square root of 1 plus 4x squared plus 4y squared. Okay? dA. All right. Now, I know in rectangular coordinates, the base is going to be easy to do. Minus 1 to 1, minus 1 to 1. And you do xy, dx, dy. However, it's a little messy in the square root because it's kind of a pain to do. So what we are going to do here, that's going to be such a big pain to do in rectangular coordinates here, we've got to change our limits, not from minus 1 to 1, minus 1 to 1. We're going to have to change those in the polar coordinates. And this really turns out to be a pain in the neck problem, but it's doable. Okay? And if you haven't noticed, this is a lot like what we had before, integral over the region R. If we do change this, this will be the square root of 1 plus 4r squared. Right? And then this will be a r dr d theta. Okay. The problem comes from getting your limits in x and y to be limits in r and theta. Okay? And there's not a particularly pretty way of doing this. But here's what we do. And it comes from this. They're going to flip things around on you. And let's go this line right here. And we're going to do an angle right there. Okay? Now, if I drew this in the xy plane, here would be the x equal 1. Okay? And we'd be doing the angle here. Okay? Now, I don't know if you remember this, but x in polar coordinates is what? Does anyone remember? R cosine theta is equal to 1. So the x equal 1 becomes r cosine theta equal 1. Okay? Which, you could say r is equal to 1 over cosine theta. right? If that would ever show up, it's not going to. Yep, there it is. Well, what is 1 over cosine theta? Secant theta. So your r is going from 0 to secant theta. Okay? Now you're going to have a sector there, 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 a sector there. So if you just take this sector here and multiply it by 4, you're going to get your area, right? So I think that's the way we need to go on this one. Okay? Now what are the angles here? Each of these is 1, 1, minus 1, minus 1. So your angle there is going from 45, exactly, because that's the square. Dissect that, it's going to be 45. So it would be minus pi fourths to pi fourths. Those are your theta limits, okay? And we're going to take that and multiply it by 4. Because this part up here, the surface area, is going to do the same thing, okay? So basically we're just doing the... Yeah, when you do add them together, it's going to 90. Yeah, this is a 90 degrees here, but we're going from minus pi fourths to pi fourths. So that is 90, 90, 180, 270, 360, you go all the way around. Okay? All right, you're just going to do 4 of those. Okay? Use symmetry. It's your friend. All right, so let's see if we can get this set up then. This will be a double integral, and I guess it's best to let, r go from, okay. And this will be 1 plus 4r squared to the 1/2 r dr d theta. Drives me nuts here. Your r is going from 0 to secant theta, and then your theta is going from minus pi fourths to pi fourths, and you're doing 4 of those. Okay? Now, don't let me forget my 4 like I forgot my 5 last time. Different reason. How would you do that first integration? Say again? Let u equal 1 plus 4r squared, right? Then du is equal to 8r dr, okay? And let's see what we've got now. We don't want 8r dr, we want divide by 8. So then you will be 4 over 8, which is 1/2, the integral from minus pi fourths to pi fourths of u to the 1/2 du d theta. Got it? I left off my integral. Okay. Say again. Oh, we got to change our limits too, don't we? Uh-oh. I'm sorry? Secant theta. See, that's what r is going to. It's going from 0 to secant theta. Okay. Now, your what's that?
Are we going to substitute for u?
That's what I was just looking at, and I was trying to figure out a way to do it. When u is equal to 0, when r is equal to 0, that's...
Can you figure out it as tangent? Is this a tangent squared?
Okay, you're getting close, okay? But where did it go, Mr. Joe DiMaggio? There we go. Okay. All right. When r is equal to 0, u is equal to 1. So that's going to be the easy one. Okay. Now what you're suggesting here, when r is equal to secant theta, we have 1 plus 4 secant squared theta. Okay? Right? Yeah. They don't do a u substitution here because it does get messy with the thetas. Can we do it without a u substitution? Just sort of thinking through it, and what we're going to do is not change the limits. Let's do the u substitution and go back to r's, and that way we don't have to change it. So let's not change these limits here yet. Okay, we're not going to change that one. What we're going to do is how we used to do it with the others. So let's do this, and that integral is going to be, what's the antiderivative there? Okay, u to the 3/2 times 2/3, okay, and then we're going to have our d theta, okay. Now, at this point, okay, let's go on and get rid of the 2's and put the 3 out here, so that's done. Now we're going to go back and plug back in here, and this is going to be 1 plus 4r squared. Okay. I'm running out of room rapidly.
You get a race to the top.
What's that?
You get a race to the top.
Okay, let's do that then, if you don't mind. Okay. Now the other thing I'm fearing is, just looking at the book, I think I've dropped another constant somewhere, and finding that is going to be a pain in the neck, especially once I've erased some stuff. So let's see if we can find it. 1/3 is now, I think. We already pulled the, well, I don't know, maybe I didn't. No, we pulled out the 1/8, but we had a 4 in front, so that left a 1/2. We had a 2/3, that made it 1/3. So I think what we got is a 1/3, the integral from minus pi fourths to pi fourths, and then this would be 1 plus 4r squared to the 3/2 power d theta. That's what I think we've got there.
Why did we pull the 4 out?
Why did we pull a 4 out?
Yeah.
Right here?
Yeah, where the...
Because we only did 1/4 of it. Right here. We're going to go all the way around to 4 of those. Okay? All right. So then we divided by 8 and got the 1/2, and we multiplied by 2/3, and that wiped out the 2's and left us a 1/3, I think. Okay. And that's where the 1/3 came from there. Now that we've got the r's in there, we need to evaluate this from 0 to secant theta. Okay. So this will be 1/3 integral from minus pi force to pi force. Okay. Okay. Now, when we put in a 1 plus 4 secant squared theta to the 3/2 power, this is driving me nuts. Okay. Okay. And then you subtract the 0 and you have a minus 1. Okay. Then this is times d theta. Okay. Now somewhere they came up with a 1/12. We have a 1/3. So I dropped a factor of 4 somewhere else, I think. I don't know where. And I was afraid of that. I have a feeling it has something to do... Oh, of course it does. I think. Hold on. Nah. I don't know. Oh, well, I see what they've done. They did the 1/4 of 4. I think it would do okay. This is where they use Simpson's rule, and they don't show you how they use Simpson's rule. Okay? And we really don't have time to go back and do that again. You can approximate the integral with Simpson's rule, and you would have to go through and do, remember how that went? Your coefficients were 1, 4, 2, 4, 2, 4, 2, and you'd have to break that into a certain thing. So this was a pain in the neck problem that they finally just stop and say, and then when you do Simpson's rule, you get this, without showing you how to do Simpson's rule, because you can't really do it any other way. I should have stopped while we were ahead and not even mess with it. But this is what you would do. Up to this point, we're okay. But what we can't do is that integral up there with anything other than an approximation. There is no formula in the book or anywhere else that's going to do that for you. So you'd have to go to Simpson's rule to do it. So I say, let's just cut our losses and stop it there. You're not going to have one like this on the test. Okay? If you do, shoot me and put me out of my misery. Okay? No. Okay. So that finishes 14.5. Homework exercises here. Do any of the odds 3 through 15. They're all at Calc Chat. 5's at Calc View. Do either 17 or 19. They're both at Calc Chat. 17's at Calc View. Do any of the odds 21 to 25. They're all at Calc Chat. 27 or 29. It's there at Calc Chat. 31 should be at Calc Chat. You can look into doing that. You don't have to if you don't want to. Then there's a surface area problem. 33 should be at Calc Chat. A product design. 35 should be at Calc Chat. Another surface area problem, and that one looks like a really big pain in the neck. 37, but it should be at Calc Chat. And that's as far as you need to go. Now, all right, to erase what's on the slide? Okay. The reason I want to do that, we're going back up here. Chapter 14, multiple integration. 14.6, the section we're going to now, triple integrals and applications. Okay? Up to now we've done single integrals, double integrals. Now we're going to do triple integrals. I think you'll find they're a pretty straightforward extension of what we've been doing. We use a triple integral to find the volume of a solid region. Okay, before we were finding, well, some volume, but then we also found surface areas. Now we're going to find the volume of the solid region, and we'll find the center of mass and moments of inertia of the solid region. We may leave off this moments of inertia, I think we did last time, and just maybe look at centers of mass. Okay? So let's do triple integrals. In fact, that's the main thing in this section, is to do triple integrals. And if we can do an application or two, we might. Okay? All right. How are we doing time-wise? Yeah. You want to go and get started on this, or do you want to go and take advantage of, since we're starting a new section, to take a break now? Or no break? Everybody's good? I can't hear. Keep going? Okay. So let's do triple integrals. The procedure used to define triple integrals follows that one that we use for double integrals, with one pretty major exception. Double integrals, we use a two-dimensional grid. Triple integrals, we use a three-dimensional grid, which is sort of a pain. Consider a function f of three variables that is continuous over a bounded solid region Q. So, not the superimposed grid that you see here, but that thing underneath the grid, that's your solid region Q. Okay? Not the box-looking grid, the solid region underneath that. Okay? Then encompass Q with a network, and that's what this is, a network of boxes that form the inner partition consisting of all the boxes lying entirely inside Q. Okay? Now obviously these out here are not inside Q, these over here are not inside Q, these down here are not inside Q, but there's also some out here that are not inside Q, but you can't tell that because the color of Q is still behind it. But there are some. So what they're going to do is take away all those, and all the boxes that are totally inside that region there, those are going to be your inner partition. Okay? Now, if you're doing the volume of all those, that would be the summation of. There's absolutely no reason that should blink out like that, because I wasn't touching anything. Okay. So now you get a series of these partitions inside that, totally inside that, and you just number those 1 to n. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, to n. All those. Each one of them has a little number with it. Okay? And the volume of the Q then is approximated by the summation of all your little volume elements there. Delta V's. Okay? Delta V sub i's, where I is going from 1 to n. Now, the volume of the ith box, not the ice box, but the ith box, V sub I is your delta x sub I, delta y sub I, delta z sub I. Volume of the ith box. The norm, just like we had before, looks like the magnitude of a vector type thing. The norm of that delta of the partition is the length of the longest diagonal of the n boxes in the partition. That's what your norm is. Choose a point, x sub I, y sub I, z sub I, in each box to form the Riemann sum. Okay? So we're going to sum all these together of the f inside the box, of the ith box there, and then multiply it by the delta v sub I, which is your rectangular dimensions. Delta x, delta y, delta z, all i's. Okay? And sum all those together, that will be your Riemann sum. Then we're going to let, as the norm goes to 0, that means your n is going to infinity. The definition of a triple integral, if f is a continuous over a bounded solid region Q, then the triple integral of f over Q is defined as the triple integral over this volume Q of f of x, y, z, dv, okay? And that would be the limit as your norm goes to 0, n goes to infinity of your summation I equal 1 to n, f sub x. So you see, as your dv is going to, okay, your delta v, as your maximum delta is going to 0, this is going to dv. Your f of x sub I, y sub I, z sub I is going to f of x, y, z. Your summation of all those n, as n is going to infinity, of all those n volume elements will be your triple integral over Q. Okay? Provided that the limit does exist. The volume of the solid region Q is given by Q is equal to the triple integral of this dv.
Is dv equal to dx, dy, dz?
Yes, if you have those things. Now, if you have spherical coordinates or polar coordinates or something else, then you do those. But the one we've described here, when you use that kind of partition, is dx, dy, dz. Exactly. Okay? That's your volume element. If I could get this to advance, it's not advancing. Okay, there it is. Okay. All right. Now, this looks a little bizarre, at least in my book. Here is the definition of your triple integral when you have a function in there. You have that. When you don't have a function, you just want the volume defined by this with no function there, then it's just the triple integral of dv. When you're trying to evaluate a function, you do the function value over that dv. Okay? Now, some of the properties of double integrals can be restated in terms of triple integrals. Number one, if you've got a triple integral over some volume q of c times some function of that dx, if that c is just a constant, pull it outside, all the way outside the triple integral, and then just do your triple integral over the function. Same answer. Or the triple integral of a sum of two, sum or difference of the two functions, is the sum or the difference of the triple integrals of those two functions, assuming that both of those are integrable. And then this one, that the triple integral of alpha x, y, z, dz would be the triple integral over q1 plus the triple integral over 2q, as long as q1 and q2 have nothing in common. They can't overlap at all. But if you did that, and they have nothing in common, and just separated by some surface there, then you can do that one. Now, they did a pretty poor job of showing that. I don't think they show it in the book at all. In these properties, Q, that last one, Q is the union of two non-overlapping solid regions, Q1 and Q2. If the solid region Q is simple, then the triple integral over that can be evaluated with an iterated integral using one of the 6 possible orders of integration. And this was part of your question. That delta v dv could be dx dy dz, dy dx dz, dz dx dy, dx dz dy, dy dz dx, or dz dy dx dz dy dx. Whichever order is going to be easiest to integrate, you can use any one of them. Okay? A lot of times it's not going to matter. Other times it might make something much easier to do. So you can order those any way you want to. Make them make sense though. Okay? Here's theorem 14.4. Okay. Haven't got to example 1 yet, but we're getting there. Evaluation by iterated integrals. That f be continuous on the solid region Q, defined by x is going from A to B, your y is going from h1 of x to h2 of x, but your z is going from g1 of xy to g2 of xy, okay? So in this one, the order is going to matter big time. The first integral you do is going to be the dz, the next one the dy, and the last one's going to be the dx. So you've got to do them in that order, dz, dy, dx. Why is that? Because z is defined between two functions that are defined in two variables, so you have to do that integration first, then follow it by the one y as a function of x alone, and then plug in for your last integration the values for x. So it does matter what order you do depending on what you know about the problem. Okay? And sometimes you'll be able to exchange these, sometimes getting better, sometimes getting worse. So let's do one. All right, here's the integral. And they've set it up for you the way you've got to do it. Okay? Just like we did before. Evaluate the triple iterated integral, which is the first integration is going to be 0 to x plus y, so that's obviously going to be a dz. The next one's 0 to x. Since we've already done the dz, this has to be your dy. And finally, your x is going from 0 to 2. Okay? Now, how would you do that integration? They've set it up for you. Only way you can do it. So, show me the money. How do you do that? Wait. Okay.
Is the e to the x a constant?
Is e to the x a constant? No, that's a function of x. Now, if you're doing your dz, you treat it like a constant. Is that what you're asking? Yes. Okay. So, what would be? Frankly, don't mess with the 0 to 2. That comes later. Don't mess with the 0 to x. That comes later. We're only going to do this innermost integration first. And what would that be?
It would be e to the x, y, z plus...
Okay. E to the x, y, z. I'll buy that one.
Plus z squared.
Plus what?
Z squared.
Okay. You still got to have the e to the x, z squared. Buy that? And for some reason, this pen is just dragging like crazy today. That is so ugly. Z squared. Okay? And that's being evaluated. Now let's check it. Let's check it. Let's take the partial of this with respect to z, and that would be e to the x, y. We got it. And the partial of this with respect to z would be 2 e to the x, z, and that should like this. Okay? We're going to evaluate this. Now, I like to write this in here. Z is equal to 0 to z is equal to x plus y. That reminds me that these correspond to the limits of z, which helps me to plug them in the right place here. And then you'll have your dy and dx later. Okay? So let's do this one now. The integral from 0 to 2, integral from 0 to x, and what will that one be? Okay. I wish I had done this. I'll show you later. Okay, go ahead. What were you going to say?
Were you about to say, like, we do anything with, like, L1?
Say that one more time.
We multiply it by L1 to get rid of the e's?
No, not that. And that's not a multiplication, that's a composition. And we can't just go and compose a function.
Can we at least get rid of the z's by putting x plus y's?
Okay, we are going to plug in for z these values here. But what I wish I had done, because you see this e to the x, you're not going to use it till the very end. So what I wish I had done was take it out here and put it here, because you're not going to do anything with it except drag it along. So consider that done now. E to the x, they're not even in there. That makes it so much easier to do evaluation. Okay? So z is equal to x. Now I'm pretty sure that's a plus y. I don't know why it's not showing up, but there it is. Okay? So we're going to evaluate that. The y stays a y times x plus y, right? You see what we're doing? Plus x plus y squared. And then when you put a 0 in for the z, you get a minus 0 minus 0, right? Agreed? Okay, so those don't contribute anything. All right, so next we're going to do our dy, and later we're going to do our dx, but not now, later. Okay? Now, and I don't know why the e to the x didn't show up here, but there it is. Okay. Now we're going to do, again, the inner integration. But this time we're integrating with respect to y. So the 0 to 2 for x and e to the x are going to still be out there. Now we're going to integrate this one with respect to y. And frankly, what I think I would do is do this.
You can multiply together the y times x plus y.
Like that?
X plus y squared.
Right. Is that fine? That's exactly what I would recommend. And this one, you want to go and expand that as well? X squared plus 2xy plus y squared. Okay? Now let's see if we can eliminate. Hey, look at that. Minus y squared plus y squared. Those disappear. And here we have an xy plus 2xy, so that makes 3xy. So we'll get that one out of there. And then
why is it a minus y?
That's a very good question, isn't it? That was supposed to be in a plus, wasn't it? Yep, you're right. So we can't do that. Okay, let me go back and correct. There we go. And let's just start over, so to speak. Okay. It's y times x plus y squared. So this would be xy plus y squared plus x squared plus 2xy plus y squared. That's not right either. I know, this is supposed to be a xy. The old gray cells are not working well today. Okay. Okay. xy plus y squared plus x squared plus 2xy plus y squared. So this new integral, 0 to x, will be x squared plus 3xy plus 2y squared. I hope that time it came out right. dy and finally dx. Okay? Goodness, my stomach is growling like crazy. I'm so hungry. Okay? All right. Now let's do our antiderivative of this one. It's going to be a 0 to 2 e to the x. That hasn't changed any. All right, let's do the antiderivative of this one. With respect to y, what would be your first term? X squared y. Perfect. Say again?
With respect to y.
Yeah, with respect to y. Okay, next. Plus 3xy squared over 2, right? Plus over 3. Evaluate that from y equals 0 to y equal x. I like to kind of write that in there to keep myself reminded that those are evaluated at the y's. Okay? So this will then be the integral from 0 to 2. We've hung that around for a long time. E to the x, we kept that around for a long time. Okay?
It's going to be x cubed plus 3 over 2 x cubed plus 2 over 3 x cubed.
Okay. Goodness gracious. Okay. So let's combine those things together. This is the integral from 0 to 2. We'll get there one of these days. Now let's combine those together. What's your least common denominator?
6.
6. So let's make this 6x cubed over 6. If you multiply this one by 3, you get a 6 down here, and that will be 9x cubed over 6. If you multiply this one by 2, that will be a 4x cubed over 6. So that will be an e to the x times, what do those add up to? 19/6? Yay or nay? 6x squared over 6 plus 9x squared over 6 plus 4x squared over 6. That would be 19, right? 19x cubed over 6. Okay? And we're going to evaluate that from 0 to x. Oh, wait, we've already done that. Sorry. Regressing. Okay. Dx. All right. Now, how are we going to do that integral?
We can pull up the 19 over 6.
Absolutely, that would be a good move. How do you think we're going to do that?
Integration by parts.
Absolutely, that's what we're going to have to do, and what a pain in the, what a joyous occasion that will be. Okay? And in the book, and this really gripes me, they do it in one step, saying, to do this last integration, use integration by parts 3 times. And that's what you got to do. Now, do you want to go back and review your integration by parts and do it 3 times, or do you just want to use the result they have in the book? Well, you show how to that. Got it? Second? Do it how we got it? Okay. I think to do this then, I'm going to erase what we've got and only put that last integral and do it, because otherwise it's going to take forever. Okay? So I'm going to erase everything. Just remember what that integral was. 19/6, 0 to 2, e to, okay. You got it? All right. So what we've got is the integral from 0 to 2 of x cubed e to the x. I'm going to write it the way they did. That's dx. Okay. Now, how does integration by parts go? Anyone remember? What's that? The table method? Okay. You want to do that? Okay. You what? You don't remember? So you're going to have me do it even though we don't remember it. Okay. What's that? It is faster if you remember how to do it. Okay. So just to, oh, you don't have a book anyway, do you? I was going to say, do you even have an ebook or anything else? Okay. If you do want to look this up on somehow and see this, it's back on page 528. Way back there, 528, back in Cal 2. What I realized the other day, by the time this term is over with, I will have taught almost this entire book. Okay, what page did I say it was? 528. Okay. Integration by parts. Integration by parts. There we have it. Okay. All right. Now, how they do this, they set up alternating signs, plus, minus, plus, minus. We might need one more, but I don't know, okay? Now, the u part is going to be the x cubed, okay? So it'd be x cubed, x squared, x. I don't think we'll need any more than that. Well, they show a 0, 1 and then a 0, okay? All right. Your dv part, or v prime part, this is the signs. This is the u part, and here's the v part. Okay, and the v part, you skip down 1, and this is e to the x, e to the x, e to the x, and e to the x. Okay? All right. Now, what's that? Yeah, well, that's basically, I've just done it. Oh, I'm sorry. Yeah, I'm sorry. I didn't take the full derivative. Okay. Okay. And then this part, they're all e to the x's. Yeah. It's x cubed, 3x squared, 6x, 6, and 0. Okay. Now, all you do is the product of those three. So that's going to be x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus 0. Okay? Now, of course, every one of those has an e to the x in it, so we'll pull out the e to the x, and that leaves us x cubed minus 3x squared plus 6x minus 6. Okay? Now, x cubed minus 3x squared plus 6x minus 6, and we evaluate that from 0 to 2. Okay? So evaluate it at 2, and what do you get? E squared times 8 12 plus 12 minus 6, and then when you plug in the 0, well, we'll come back to that in a minute. Yeah, you'll get a minus 6, so it's going to be a plus 6, right? Okay. Now these add to be 2, so this will be 2e squared plus 6. I think is what you get. Oh, wait. Huh. You were supposed to remind me of this. 19 over 6. Okay. So this is times 19 over 6. Okay. Now, what they did here, which is okay, the factor out a 2 from here, and this will give you a 3 here, so it would be 19 thirds times e squared, e squared plus 3.
Yeah, I did all the integration by parts.
What's that?
I did the whole integration by parts. It took 3 times.
Yeah, exactly.
I got the same answer.
You got the same thing. Good deal. Okay, and if you figure out what that is, now actually in the book they wrote it differently. They did 19 times e squared over 3 plus 1. Either way you do it, it's going to come out the same answer. And they came up something about 65, right? Now, are we out of time? No, we're not, are we? Oh, I see. Okay, I was going to say, woo, time couldn't have flown by that fast. Okay, sorry I didn't have your test ready today, but I'll knock on wood. Okay, now here's another thing. If you're on campus tomorrow, let's see, let me say afternoon. Hopefully I'll have your test ready by then. Are you, either of you come to campus at all on Thursday? I know Nolan does, but you won't be here in the afternoon, so you don't come either. Nolan, are you here later in the afternoon or just in the morning? Okay, well, I'll try to have it ready for you Monday then. I was going to say, I hope to have it ready tomorrow afternoon, but if y'all won't be here, I won't bother with it too fast. I'll just get it done. Okay. All right. Good deal. Now, okay. Rather weird problem why they came up with it. So weird, I'm not sure, but it works. Okay. Now, let's watch and see how they do it. Okay? All right. For the first integration, hold the x and the y constant, integrate with respect to z. Now, what they did, they left the e to the x there always. There's really no reason. Take it and put it here inside the dx integral, but then you won't have to mess with it. So this would be yz plus z squared. And that's what you get here, with e to the x out front. Evaluate that from 0 to x plus y. Now those are the values for z that you put in there. And when you do that, that would be integral from 0 to 2 of integral 0 to x of e to the x, which you could bring out in between those two, of y times x plus y squared plus, and this is where you do all those things, x squared plus 2xy plus things. So that came out x squared plus 3xy plus 2y squared, dy dx. So the next integral you do with respect to y, again, the e to x go on the outside, not all the way out, but just outside that next one, and then integrate only that part there. And hold the x constant and integrate with respect to y, get the e to the x out of there, out to the next one, and that would then be x squared y plus 3/2 xy squared plus 2y cubed over 3. Evaluate that, 0 to x. Now, when you plug in y is equal to x and y is equal to 0, y is equal to 0 contributes nothing, but that would give you e to the x, and that would be y cubed plus that's the same one we got, so I'm not going to go through it again. But you get this 19/6 integral from 0 to 2 of x cubed e to the x. And then you integrate with respect to x, and as they say here, that gives you, well, they don't even say it here, but when you did the integration by parts 3 times, that's what you get, which is about 66. Okay? Now, jumping the next rabbit here, to find the limits of a particular order of integration, it is generally advisable first to determine the innermost limits, which may be functions of the outer two variables. Then, by projecting the solid Q onto the coordinate plane of the outer two variables, you can determine their limits of integration by the methods used for double integrals. Okay? So, take a look, evaluate, see which is going to go first. Which most easily goes first. To evaluate this one, the triple integral over some volume Q of f of x, y, z, dz, dy, dx. The way they have it set up now, you better do your functions here. It should be a function of x and y, because you're evaluating with respect to z. You're going to leave the x's and y's in there and just integrate with respect to z. Then this one could be, have x's in them, functions of x, f1 of x and f2 of x. Could, may not, but it could. And then the last one, though, can only have numbers as their limits. Okay? Now, here is your solid Q, projecting that onto the xy plane. This is what we're trying to evaluate here. Project it onto the xy plane. In other words, imagine you have a light way up there shining down on it. What is the shadow in the xy plane? That's projection into the xy plane. Now, the lower surface here, this one down here, is some function g of x and y, because here's your xy down here. And then the upper surface is some different g, g2 of xy. And you're trying to get the volume of this solid Q in between that. Solid region Q lying between those two surfaces. Okay? Once you get between these two, it looks like, as far as I can tell, it's not going to matter. If this is a rectangular solid here, you can do y going from some function of x to another function of x, especially if those aren't done. Now, if those are just numbers, and that's a number without having a function involved, you could just use the numbers. It looks like to me that angles aren't quite the same, so I think you probably would need some function. And then you finally do the x, the integrate with respect to x from whatever this value is here to whatever this value is here. Okay? So that would determine which way you go. Now, all that being said, they're skipping example 2, which shows this, and example 3, which shows this, and example 4, which shows that, to get the center of mass. So let's go back and do examples 2, 3, and 4. And unfortunately, that probably means I have to draw some pictures. And that's going to be really ugly. Let's see if I can get a little more white space. No, I can't. Okay, we'll just use that. Okay. Oh my goodness gracious. Example 2. Find the volume of the ellipsoid given by 4x squared plus 4y squared Goodness gracious, I've got to sneeze. Y'all awake yet? All right, good. I have to do it every now and then just to make sure y'all stay awake. Okay, I'm going to have to go it again. Plus d squared. Wait. Okay, just in case you fell back asleep. Okay, is equal to 16. Now, that's not my favorite expression of an ellipsoid. If I were doing this, I would divide everything by 16 and have this x squared over 2 squared plus y squared over 2 squared plus z squared over 4 squared is equal to 1. Okay? And with that in place, you know the z-axis is going from minus 4 to 4. The y and the x are both going from minus 2 to 2, if it's the entire ellipsoid. However, since it's located at the center, everything revolves around the center, you can just do the first octant and basically go 0 to 2 on x, 0 to 2 on y, and 0 to 4 on z, and multiply that by 8. Okay, 8. Because all of those volumes are the same. So that's going to be the easier way to do it. Now the question is, how do you do your integration? And again, everything is pretty symmetric, so it's not going to matter so much. I wish they had the figure so I wouldn't have to try to draw this. Okay? It says here, because the x, y, and z play similar roles in the equation, the order of integration is probably immaterial. You can arbitrarily choose dz, dy, dx, but it doesn't matter. Any one of those will do. Moreover, you can simplify the calculation by considering only one portion of the ellipsoid lying in the first octant, multiplying that by 8. Okay? So, here's what you do. If you're just considering the first octant, so everything's going to be positive here, and you're going to do your dz first, that's just what they chose to do, then what is z going from? Well, let's solve for z. Z squared is equal to 16 minus 4 squared, 4x squared, minus 4y squared. Okay? So z in the first octant is going to be the square root of 16 minus 4x squared minus 4. What's that? Perhaps at some point. Okay? Right now, let's just deal with them as they are. For the x's and y's here, yeah, that's coming up very good, close to an r squared here. But they don't do that, and there may be a reason for it. I can't think of what it would be right now, but this is how they're approaching it. So anyway, z is going from 0 to this value here. Okay? Now, there is something else you can do here. Every one of these factors has a 4 in it, so you could take out a square root of 4. That would be 2 times the square root of 4 minus x squared minus y squared. Okay? So z is going from 0 to that value right there. Okay? So that would be your limit on the z. All right. Volume of the ellipsoid would be the triple integral over that region Q of, well, let's, hold off for a second here. Let's not go back to Q again. The Z is going from 0, oh, and you're going to have 8 octants, so you got 8 out front. Don't let me forget that. From that to 2 on the square root of 4 minus x squared minus y squared. Okay.
Why is it 8 again?
What's that?
Why is it 8?
Because, okay. Well, rather than have to draw the picture, let me show you the picture. Okay. Okay. Here's the ellipsoid. It goes from minus 4 down here to plus 4 here, minus 2 on x to plus 2 on x, minus 2 on y to plus 2 on y. Everything's symmetric about the origin. So if you just do the first octant here, you're going to multiply that by 8. 1, 2, 3, 4, 5, 6, 7, 8. So they're all going to be the same size. Now this doesn't quite look like they are, but that's because it's a 3-dimensional projection onto a 2-dimensional page. But indeed, they will all be the same. So now your limits for x are going to be 0 to 2, for y is going to be 0 to this value here, and z is going to be 0 to the value up there. So that's what we did. We found out what the value up here is. When you solve for z, that gets you up to that point. Now we're going to be doing y from 0 to this. But because you're only doing from 0 up, you need to double it for this one down here and triple it for that. Yeah, you have to. All right. Sorry, it just needs to get, sorry. Okay. I don't know why this is coming on, but it's loosening everything up. All right. Now, you're just doing a volume here, so it's just the integral of dv, okay? And your dv here is going to be, we're doing the dz first, then we're going to do the dy just because they chose to, and then the dx, okay? Now, let's do the dy's next, okay? Now the dy, again, is going from 0, and once you've taken care of the dy, I mean the z, and that's out of the picture, you're going from, if you, kind of like you're solving this for, you've gotten rid of the z's now, not the z's, but these z's, okay? Your y, if you solve that for, that would be y squared is equal to, I believe it's 4 minus x squared. Let's see if that's right. So y is equal to the square root 4 minus x squared. I think that's right. Let me check. Yeah, that's it. So the y goes from 0 to the square root of 4 minus x squared, once your z is out of the picture. And then your x is, the last integral is going to go 0 to 2, because you're just doing that first octant, 0 to 2, okay? Now, the antiderivative of this thing dz is just going to be a z, and the z is going from the upper, from 0 to the upper, so that is basically, it's going to be 8 times the integral from 0 to 2 times the integral from 0 to the square root of 4 minus x squared. And then this will be, the 2 goes in there, so let's pull the 2 out and make this a 16. and then you'll be doing the integral from 4 minus x squared minus y squared. Okay? dy dx. Okay. Now, here again, they kind of drive me nuts here. Okay? They rewrite this as this. The square root 4 minus x squared minus y squared. Because you're taking the derivative with respect to y here. So this is all counted as a constant. Okay? They go to the table, okay, the integration table, in Appendix B, whatever book you have, you can find it wherever that is. You're going to find an integration table somewhere in the book. I'm pretty sure. I've never seen a calculus book without one. And in this book is formula 37, and that gives you an arc sine. Okay? Now, it involves a 1/2, and just from out of nowhere, then they start fiddling with this, and so with the 1/2, the 16 goes back to being an 8, so that would be an 8 times the integral from 0 to 2, okay, and when they plug that in, when you go to the table, what you have left over is a y times the square root of 4 minus x squared minus y squared, or minus x squared minus y squared. Sorry. The pen gets so slow toward the end here, it's hard to keep up. Plus 4 minus x squared okay, times the inverse sine, they do arc sine, but it's the same thing, of y over the square root of 4 minus x squared. And evaluate that from 0 to the square root of 4 minus x squared. Okay, and then you'll have your dx out here. And you see I've run out of room again, and you've got to integrate this thing, which is a monster of an integration. Okay. When you're evaluating, these are the values for y. So you put this in for y here. All those stay the same. You put that in for y here, so you lose the square root. Okay? And you put it in for y here. That thing there, so you still keep the square root. Okay? And that gives you an outrageously complicated, well, not that bad, complicated function of x, and then you've got to integrate that. Okay? And again, it just is writing down what's in the book without very much justification, because they're skipping step after step after step. But when you do it, it all comes out. Now, the good news here, by the way, this is your numerator here, and that's the same as your denominator. So that's going to be the inverse sine of 1, which is pi halves, right? And that's pi halves times that. And then this will be the same, well, no, it's not quite the same thing. And so that still leaves a lot to be desired. And, oh, well, let's see. When you plug this in here, you get the square root of 4x squared minus 4 plus x squared. So some things do simplify pretty nicely, and at the very end, the answer is 64 pi over 3. I'm not going to continue doing that. It's just I don't have room for it, and by the time I erase it, you don't see where it came from anymore. So let's move on to example 3. Okay? Now, this is one that you will choose, as they say here, to change the order of integration, because it really becomes a pain in the neck if you don't. So here's what they say. Evaluate this one. The integral from 0 to root 2 over pi over 2 times the integral from x to root pi over 2 final integral 1 to 3 sine y squared dz dy dx. Okay? And in the first place, this is a stupid way to write this problem. Okay?
Is that the square root of pi over 2?
Square root of pi over 2, exactly. Okay? And here's why it's crazy to write it this way. You don't want numerical integration here, limits here, before you've done your variable integration. So this needs to be here, and so your dy had better be the first one you do. Okay? Now, after that, it really doesn't matter as much because both of these have numerical values, but the really bizarre thing here is trying to get this to integrate. Okay? That is not a particularly pretty thing to integrate. If you had a y somewhere here, that would be fine, but you don't have that. So what would you use there? If they say Simpson's rule, I'm going to scream at them. Now, what they say to do, because that is not an elementary function, it has no integration, sine of y squared. It doesn't. It said to avoid that problem, change the order of integration to dz dx dy so that the y is the outer variable. Okay? Now, all this depends on the shape of your solid. Okay? Now, and if I could draw this thing, I would. I'll try to. let me see if I can represent this well. Your z, no guarantee on this. Here's your x, there's your y, and there's your z. Okay? It's actually too many. I could have left it. Okay. 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 3 on Z. Okay. If you got a calculator, punch this in for me. Square root of pi halves. .25. So that would be 1, 2. So somewhere about right in here is the square root of pi halves. And so somewhere down here would be the square root of pi halves. Okay? Now, the other boundary here is x. Y is equal to x, and that would be somewhere here. Okay, so this would be, okay. Okay, this is a really ugly drawing. Okay, it's something like this, okay, something like this. Let me get this line out of there because that's really messing up. And this is a terrible drawing, but it's the best I can do given the situation, okay? Now, this function here, this is what you're trying to evaluate this over this volume, okay? So this has no play in the volume any. This is what you're trying to evaluate that over, okay? So that sounds a bit bizarre. Okay, and I think I'll take out this line too because it's not really contributing anything either, okay? So that projected downward would be there. Okay, let me get my pen back. Okay. Well, I went and did it again. I don't need that. I was just trying to make sure I was at the right place. Okay? Now, really ugly drawing, I understand that. This is the line y is equal to x. Okay? And the way they have it set up is you're evaluating this function, which is a non-elementary function, and z is going from 1 to 3. Okay? Your y is going from x, that's y is equal to x, to y is equal to the square root of 3 over 2. So basically you're doing your little increments here from x to no. I think it's going the other way. No, that's how they said it's going. Okay. That doesn't really look like it makes sense that way. Looks like to me they're going from this line to that line. And that would be from x to square root of 3 over 2. So I think they've got it wrong. Okay. And then finally, the x is going from 0 to root 2, and that would be this way. Okay. So I think they showed their picture a little bit backwards. Okay. That's what you're doing. Let me clean it up just a little bit. Okay. Okay, so now to get the picture of it. Your z is going from 1 to 3, that's solid. Your y is going from x, here's y is equal to x, to y is equal to square root of pi over 2, and then your x is going from 0 to square root of pi over 2. That's going to be your last integration. Okay, they drew the rectangle in the wrong place, I think. Okay, so that's your setup here, but you don't want to lead off. Okay, your first integration wouldn't bother you of this, but your next integration would. So they say put this off till the very end, because then you will be just substituting it. Well, let's just see what you're substituting. You certainly can't do it with the way it is now, okay? So what they're saying is, let's rearrange these and do a d, I would say dz last, but they do the dy last, dz first, dx next, and dy last, okay? Now, because the dy is last, you can bring your sine of y squared out there. And this is still going to be, okay. But let's think about what we're doing now. If you're doing the dy last, then your dx is going, oh, I see what they were doing. This is how they set it up. How we want to do it is going this way. So your dy is your last one to do. So this is going to be your integral. So now we're not going to do it the way they drew to begin with, which is I was trying to replicate what they were doing. Here's what you're going to do. So your last integration, you'll be going from 0 to pi halves on the last one, 0 to the square root of pi halves here. The next one is going to be your dx, and what your dx is going from is from y, reverse this and make x equal y, so that would be x going from zero to y, okay? That's where the magic is going to come to play, okay? And then your final dz is going from 1 to 3. So, yeah, you can do that one there, okay? Now, and then, yeah, we brought the sine of y squared out there. So, actually, you can now do your dz, dx, dy. Okay. Now, this is going to be the integral from 0 to square root of pi halves, integral from 0 to y, and then here's this one. It's just going to be z evaluated from 1 to 3, right? dx, dy. Okay? Well, this is going to be 3 minus 1 is 2, so we'll, forgotten left off my sine of y squared here, and that 2 we can bring out here now. Okay? So we've done that one. I need more room, so let's come up here. 2 times the integral from 0 to square root of pi halves, sine of y squared. Okay, now we're going to do this one. The integral from 0 to y of x. So that's just going to be x. So that would be y minus 0. Okay, and then you're going to have your dy. Okay, that's going to make a lot of sense now, because let u equal y squared, du is equal to 2y dy. We'll bring that 2 back inside here, so it's right where you want it, 2y dy. So now what you have, this is your integral from 0 to the square root of pi halves of sine of u du. Okay? Oh, I needed to change my limits too, didn't I? Okay? When y is equal to 0, u is equal to 0. When y is equal to root pi halves, then u is equal to pi halves. Oh, doesn't that make a nice integration there? What's the antiderivative of sine u du? Negative cosine u evaluated from 0 to pi halves. Okay? Now, I have a bug crawling in my eye. Okay? What is cosine of pi halves? Second? 0. Okay? Minus cosine of 0. Minus a minus is plus. Cosine of 0 is 1. Okay? All that, and that volume is 1. That value is 1. That's it. That's all. Okay? It's 1. Now, the key here is this was a non-elementary function you can't evaluate. So normally you would think, get rid of it first. You can't get rid of it first. So do it last and hope that you get a y in there, which you indeed do if you set it up this way. And then once you got the y in there, that becomes a u substitution that you can do pretty nicely. Okay. Whew. Goodness, what a pain. Now, they didn't do a u substitution, but it works well if you did. Okay. Now, let's do example 4. All right to erase? Okay. Now, they say the problem here is determining the limits of integration. Let's see what we can do. Set up a triple integral for the volume of each solid region. Okay? The first of these is the region in the first octant bounded above by the cylinder, z is equal to 1 minus y squared, and lying between the vertical planes of x plus y equal 1 and x plus y equal 3. Why don't they show us the pictures? Okay, this is such a pain to draw. Okay? All it says is set up the triple integral. It doesn't say solve it. So here we have, let me see if I can draw this one. This will be the z, that will be the y, and this will be the x. Okay. And for some reason the x wouldn't draw. There we go. All right. Now, the region in the first octant bounded above by the cylinder, z is equal to 1 minus y squared. So z is equal to 1 minus y squared. X does not really look like it's in the picture here. Okay? That would be a parabola with a vertex z of 1, okay, one minus y squared would be opening downward That's not a very good parabola. get a little more curve in it. Something like that. That looks a lot better. Okay. Okay. And you bring that whole thing out here. Okay. Okay, something like this. So here's your curve that does like that. Okay. Pretty ugly rendition, but that's what you got. Okay. Lying between the vertical planes, x plus y is equal to 1. X plus y is equal to 1. That would be this line right here. Okay. Oh, I'm sorry. And x plus y is equal to 3. Not done a good job here. Let me reduce this a little bit. It means redoing just about everything I've done. Okay. Well, okay, let me try something else. Okay, let's do 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. All right. If you had included it all here, this would be the parabola that looks something like this, okay, and something like this. Okay, something like that, and it would have been back here like this. That would have been the cylinder, or portion of the cylinder. Okay, this line right here is z is equal to 1 minus y squared. Okay, that's the parabola. Okay, now it doesn't go there. It's going from this angle here. So this part is kind of cut off, okay? So it's sort of doing like that. So you don't have this end over here, not the whole way, okay? Now it's going from that one to x plus y is equal to 3. Well, that would be going from this point to that one, okay? But it doesn't go nearly that far, so this is basically let me change this, the way this looks. Okay, and you're going from here over to there. So basically you're going from this place, yeah, something like that. That's a pretty ugly drawing, but it's somewhat similar to what they have in the book. Okay, this part out here, I had to draw it just to get it to go in the right direction, but that's the part we're really interested in. Okay, now, set up the triple integral for the volume of each of the solid region. Okay, your very last integral I think will be your, they show it as being the y. And I guess that's okay, because, okay, this one down here, here is the cylinder, and we're going from x plus y equal 1 to x plus y equal 3. This is x plus y equal 1, this is x plus y is equal to 3. Okay? Both of them have slopes of 1. Okay, now, they show that your last differentiation is going to be the dy. Okay? And the dy is going from 0 to 1. Okay. The one before that would be your x, and x is going from, if you write this way, x equal 1 minus y to x equal 3 minus y. So the next integral will be going from 1 minus y to 3 minus y. So that's going to be your dx. Okay? And then the first one would then be the dz, and dz is going from z is equal to 0 to z equal 1 minus y squared. Okay. That's how they illustrate doing this. Okay? The last thing, the first one you're going to do is z is equal to 1 minus y squared, and that's going from 0 to that curve there. Then you're going to do your dx's here, and the dx's will be going from 1 minus y to 3 minus y, to this one, okay? And then the last one, the y is going from 0 to 1, okay? Now, that's how I think we set it up, and let's see what they do. Triple integral of 0 to 1 minus y squared dz, one before that is 1 minus y d to 3 minus y dx, and the final 0 to 1 dy. That's it, okay? Kind of a pain in the neck, right? Okay. Let's do the B one. Let's see if it gets any better. Okay. This is 4B. The upper hemisphere of z is equal to 1 minus the square root of 1 minus x squared minus y squared. I don't know why it made a dashed line there, but it did. So here's what we're dealing with now. Z, y, x. Okay. This is a hemisphere, a unit hemisphere, going from 1 to 1, minus 1, minus 1, and 1. Okay? So here's your circular base, the unit circle, and here's your hemisphere going up like this and up like that. That's the hemisphere. It's a pretty ugly looking hemisphere, but you get the general idea. Okay? Now, the surface here, z is equal to the square root of 1 minus x squared minus y squared. Okay? Now, it really doesn't matter what you do first, but what you do last. It matters what you do first. That's going to be this one. Z is equal to 0 to z is equal to the square root of 1 minus x squared minus y squared. So that's going to be your dz. That's going to be the integral you do first. The next two, it really doesn't matter the order. So, frankly, if you're doing this, the volume of each solid region, what I would do was 4 times that, because that's only going, let me move the 4 further out because it's going to be outside of everything. Okay. Now, the next integral you do, and it doesn't really matter which order you do these, okay? But I did the 4 out there because let's do, if you do a dy here, you're going from this integral would be from 0 to the square root of 1 minus y squared. Okay? So if that's the one you do next, that's going to be your dx. So that would be 0 to the square root of 1 minus y squared. That's your dx. And then your last one, the y, is going to be 0 to 1 dy. Now you could have reversed the order of the dx and dy, but then it would change the upper and lower limit. Let's see how they did it. They did it exactly that way. 0 to the square root of 1 minus x squared minus y squared. Now they didn't do 4. They didn't do that. I did that part. So they're doing negative 1 to the other. Don't do it. Just do 4 times 0 to 1 and then 0 to the other. So use symmetry when you can. That's the same answer they'll get. Okay? Now, I think we have time for the C part, don't we?
What time do we get out of here?
What's that?
What time do we get out of here?
8:30. No, I'm just kidding. Okay. 5:25. Yeah, so we got time, right?
Yeah, we got 8 minutes.
Yeah. So let's try to do the C part. Hopefully it won't be any worse. Okay? The C part says the region bounded below by the paraboloid z is equal to x squared plus y squared. That's bounded below by that, and above by the sphere x squared plus y squared plus z squared is equal to 6. X squared plus y squared plus z squared is equal to 6. Now, what a weird thing that is. Okay? Now, what we have to do on this one is find the point of intersection. Okay? And this is sort of set up, it's going to be the curve of intersection, set up pretty well because what you can do is plug in x squared plus y squared equals z squared here. So this, z, that'd be z plus z squared equals 6. Well, let's change that around a little bit to be z squared plus z minus 6 is equal to 0. Okay? Now, this isn't how they're approaching it. And let's see, I guess their way may be better. Okay. Let's back off a moment here then. We're not going to do that. Okay. Let's do the curve. The lower curve is this one. The upper curve is this one. Z squared is equal to 6 minus x squared minus y squared. Okay? So Z is equal to the square root of 6 minus x squared minus y squared. So this is going from this curve below to that curve above. Okay? Now, if you drew the picture of this, it's going to be ugly, but that's what it's going to be. They say here the sphere and the paraboloid intersect at z is equal to 2. I'm trying to see where they got that. Okay, I would have thought what I was trying to do there would have worked for that. Trying to see why that would be 2. So far, I'm not seeing it. Well, why they use the square root of 2. They say the sphere and the paraboloid intersect at z is equal to 2. I'm trying to see why that's true. Maybe let's go back to what I was doing before. I may have been on the right track. They sort of left you hanging there, but let's do. What I did before was z squared is equal to 6 minus z. So z squared plus z minus 6 is equal to 0. Let's solve that. That factors, yeah, this is where they got it, is z plus 3 times z minus 2, right? You see that? Okay. Now, what is the point of intersection? Either z is equal to minus 3. Well, that's somewhere below. We're not even down there. Or, so that one's out, or z is equal to 2. That's where they got that. Z is equal to 2. Okay. Now, if z is equal to 2, x squared plus y squared is equal to 2, and this other thing here, so what that gives us is okay, you got your paraboloid coming up here like this and like this, okay, something like that, okay, and then your sphere is up here at z is equal to 2, okay, so you have a sphere on top here and the paraboloid on the bottom there. That's pretty ugly, but that's what you got, okay? So if the volume inside that has got to be, your innermost thing is going to be from z is equal to x squared plus y squared to z is equal to the square root of 6 minus x squared minus y squared. That's the upper limit there, there's the lower limit there. And this is going to be a dz. Okay. Now, here's what they've got otherwise. Since the curve here, the projection down here into the xy plane here, this is x, this is y, and this is z, since z is equal to the square, when y is equal to 0, z is equal to x squared, okay? And if z is 2, x has got to be the square root of 2. So this is going to be going from minus square root of 2 to the square root of 2. This will be going from minus the square root of 2 to the square root of 2. Okay? That's going to be the circle down here that this is projected onto. Now, it's a pretty ugly circle, but you get the general idea. Okay? Now, again, there is absolutely no reason not to use symmetry. So this is going to be 4 times, and it doesn't matter which way you go first. Let's just do your d like this and do your dx next. And the dx is going from I believe that's going from a 0 to y squared, isn't it? And your x is then going, your y, your last one, dy, is going from 0 to root 2. Okay. Oh, they did it in the opposite order we did. I did. And that's my upper limit here. I'm sorry, we've run out of time. That's a circle there of, that circle down there is x squared plus y squared is equal to 2. So that would be your x is going from x equal 2 minus y squared. X squared is equal to 2 minus y squared. So x is equal to square root of 2 minus y squared. Yeah. So this would be the square root of 2 minus y squared. Now I just did 4 of them. They didn't do that. I think we've run out of time, haven't we?
Yes, sir.
So next time we'll pick up with center of mass and moments of inertia. We'll at least do the center of mass. And let me give you homework exercises here. Any of the odds 3 through 9, they're all at Calc Chat. 3 is at Calc View. 11 is at Calc Chat. Any of the odds 13 to 17, they're at Calc Chat. And I think that's as far as you need to go this time. Well, no, I think maybe you can do 19 to 23. They're all at Calc Chat. 19's at Calc View. And 25 to 29, they're all at Calc Chat. 25's at Calc View. And 31 or 33, they're both at Calc Chat. 35's at Calc Chat. And stop there. We'll pick up the rest of them later. Okay. Now.
Quick question.
Yes.
So as far as final, how far is the final, like, material-wise going to go?
Okay. I know I'll go through 14.6, which is what we're in now. And let me see. I don't know if I'll
Moment
do.
of inertia, I remember that. That's I of x equals, like, I of x equals the double integral of y squared, right?
Say that one.
I of x,
I of x.
inertia.
Oh, yeah, right. Okay, yeah. Yeah, I hadn't gotten to the center of inertia yet, but yeah. Going back to that, since you asked about it. Surely they show it somewhere here. But yeah, that's what center of inertia is. And they show how to operate with them. So I think they just move you back to the previous sections to do that, because that was done earlier. I can't remember where. Cal 2 maybe?
I did it in statics. So.
Huh?
I did it
In statics, okay, yeah. But we won't do 14.8. I may show you 14.8 on the slide, Jacobians. We may do 14.7 on the slide, but I won't ask you that on the test. The vector analysis, I'd like to at least introduce you to that, but it won't be on the test. Okay. So only through 14.6 on the test, and then however far we get. You see, I can't project how far we're going to go, so I can't put too many questions out there if we don't get there. So, yeah. So 14.6. Yes.
I'll see you tomorrow.
Okay. Bright and early, or at least early.
I'll be there.
Okay.
8:45.
Good deal. Bye. All right, thanks. Good to get that in.